Hello again, this is Dr. Jenkins, and here we go for yet another body system. So this chapter we're going to cover the skeletal system, so not just the names of the bones themselves, but we've got to talk about the bone cells, how bone grows, how bone heals, and just the general structure of compact bone versus spongy bone. And then of course, we couldn't have a discussion of bones without talking about how the bones come together, which of course is the joints. So here we go. I think if you've read my bio on Blackboard, you do see that my background is sports medicine. So I've been an athletic trainer for almost 20 years. It's hard to believe. So injuries interest me. These will not be on any kind of quiz or exam, but not fun to be these people, right? Definitely not. This is a really interesting one. You don't see this very often in sports. You're more likely to see a fractured femur on something like a car accident. Oh, before and after. Oh, not good. Not good. This is the famous knee injury. Hopefully I'm educating you on old school sports, because I'm an OG sports fan. This ended Joe Theismann's career, quarterback for the then known to be Redskins. This knee should not be going in that direction. It should be going down here. We have injuries that can happen to different age groups. So this is a Colles fracture, more common in kids. Fracture of the distal, ulna and radius. And of course, I've fallen and I can't get up. In all seriousness, something like a fractured hip is more common in older individuals. All right, that was just extra. Let's get started. Let's just go. Here we go. Okay, so you know the basic functions of the bones. I mean, pretty simple. The bones function for protection, right? And support. Let me start with support. Our bones hold us up. Our bones, our legs, our arms, our legs hold us up. Our arms give structure to our muscles of our upper body. And because they work with the muscles, it allows us to have movement. When certain segments, bones work together to move. So we know those. And if you think about it at all, you can understand the function of protection. Our rib cage are bones that protect our heart and lungs. Our skull is a bone that protects our brain. So these are the main functions of the skeletal system. But there's something else here. And I want to point out this first one because it's a biggie. Inside certain parts of our femur, which is our big leg bone, and our humerus, the ends of those long bones produce blood cells. This is where the bone marrow is, folks, the red bone marrow. And the red bone marrow produces red blood cells, which of course transport oxygen in our bloodstream, as well as our white blood cells, which help our body fight infection. I can't think of a more important function. Holy moly, right? Produces blood cells, so that's really important. And then, of course, we know that calcium is a big component of bone. And mostly, even though it does give some support, the bones act as a large storage tank for calcium. And to a lesser degree, we can store some fat. That's what yellow bone marrow is, inside bone. You don't need to know that one. But everything else, please review. All right. We are going to go through, in a pretty detailed way, the structure of bone, of skeletal tissue. Okay, stay with me here. The good thing about this is it's straightforward, right? But on the other hand, there are quite a few terms. So make sure that you're spending enough time on this to familiarize yourself with all the terms. Okay, so pretty simply, and I want to start with the epiphysis. the end of each long bone, we're talking about long bones, humerus, femur, tibia, fibula, ulna, radius, even the bones, our metacarpals and metatarsals on our hand and feet, these are considered long bones. They have an end section at either end, and the end piece is called the epiphysis. I remember this simply because they both begin with an E. The epiphysis is the end of the bone on either end. The type of bone tissue inside the epiphysis is spongy bone. Look up here. It looks spongy. It would be the same thing down at the bottom end, made up of spongy, sometimes called cancellous bone. On the other hand, the central shaft is called the diaphysis. The central shaft of a long bone is called the diaphysis, and it is made up of compact bone. So just lining either edge is compact bone. It's thicker. It's not spongy. All right, so take this slowly. There's a lot of terminology, but it's very straightforward. So if you can learn and memorize it in pieces and then repetition, right, over and over and over again. Now, there is an outer covering, as there is an outer covering to every type of organ in our body. And of course, a bone is an organ. The outer covering is called the periosteum. It's pointing to it here. Covers the whole thing. If you want to try and help yourself, peri as a prefix means surrounding, like a perimeter surrounds. So the periosteum, osteo means bone. This is a very important outer covering. It has a very rich blood supply, which is a good thing. One thing we're going to talk about is that bone has a very good blood supply. And that means that it can heal really well in almost every instance. So it's a good thing. All right, so we're first going to focus in on that central shaft, which as we just described, the central shaft is the diaphysis. And it is made up of a thin layer of compact bone on either end. Okay, terminology, folks. So we just described the compact bone is what lines either edge. It's on this side too. And then there's a cavity in the center. This cavity is called the medullary cavity. In the medullary cavity, we have blood vessels. But in the medullary cavity, we also have yellow bone marrow. It's not shown that well, but filling in much of this medullary cavity is a yellow kind of spongy material called yellow bone marrow. And this is, as I mentioned before, and here I am going to bring it up so I'd like you to know it. The function of yellow bone marrow is a storage for fat. It's a little bit different than the adipose we store underneath our skin or around organs that we use for energy, insulation, protection. It's a little bit different, but it is indeed a type of fat. Okay, you can see here that compact bone that lines the edge is very strong. So we rely on that compact bone to give strength. It's very dense, it is very strong. So the function of the compact bone is just straight up strength. All right, we are only beginning, folks, with the anatomy. So if we zoom in on that compact bone, right? So from here to here is the compact bone. If I go back a slide, we're just zooming in on one little area. And if we magnify that one little area, it looks something like this. So there are a couple of things that you may notice. There is some spongy bone on the inside, not much. So even though there is a little bit of spongy bone here in the diaphysis or central shaft, we're going to keep it simple because the most of our spongy bone is in the epiphysis or the end of bone. Now, if we look at the compact bone, it is made up of these cylindrical tubes called osteons, right? So they kind of look like this, And indeed, when we look at this tissue under a microscope, the compact bone, it kind of looks like a tree trunk. If you look up top here, it looks like each one of these circles is like one of a tree. If you cross a tree trunk horizontally and you look at it, it has all these circles. Well, in this case, the circles are called osteons. And each individual osteon actually runs the whole length of the bone. These are exactly what give the compact bone its strength. Because these osteons, just think of them as really tall, strong pillars. You know, if we have like a big old Victorian house or something, or a big building like on Wall Street, we have those big pillars out front that run up and down vertically, and they just give support, they give strength. Here's another view. So we get a good look at each of the, I'll use red, each of these osteons. There's one, there's one, there's one. And they indeed run the whole length of the bone, side by side, giving a lot of strength. Compact bone. Another real life example can be like rebar. So even if we have concrete, because we do, this compact bone has collagen in it, thick protein fibers, it has calcium. So imagine that like the concrete, but in amongst the concrete, we have these steel vertical bars. So much like a compact bone, those steel vertical bars of rebar are very similar to the osteons. And this leads us to the strength of the diaphysis. So bone, compact bone, we know the compact bone lines the diaphysis. And because it runs the whole length, in this case vertical, it gives a lot of strength to up and down forces. That's why these bars are longer. And I gave you the example of columns for a building. So imagine an osteon like this, which makes the building very strong from compression forces up and down. On the other hand, the compact bone is relatively weak from side to side forces. You know, if we took a backhoe and started whacking at it from the side, it's going to be a little bit weaker. So we rely on the osteons for that compressive up and down force. That's where it is the strongest. It is not as strong to a side to side or a twisting or rotation force. We rely on a different part of the bone for that. As we're going to find out, that's what we rely on the spongy bone for. The spongy bone isn't going to be quite as strong to the up and down forces, but it is a little bit better with strength to the side to side forces. All right, so we've talked about the diaphysis, which is lined with compact bone. The inner cavity is called the medullary cavity, which is filled with yellow bone marrow, which is a type of fat storage. Now, let's go back to the epiphyses. Epiphyses is plural, but each individual end is called an epiphysis. Let's talk about the epiphysis. We already know the epiphysis is filled with spongy bone. Not the compact, dense, it's more spongy. The actual bone tissue that makes up that spongy bone is something called trabeculi. So, you know, whereas we paired osteons with the compact bone, right? The osteons were those vertical pillars, osteons, compact bone. We want to pair together trabeculi with spongy bone. Trabeculi are little pieces of bone that make up that spongy bone. Now, mixed in between the spongy bone is red bone marrow. It's kind of hard to see here, but let me just fill it in so there's no confusion. Filling in the gaps between the open areas of the spongy bone is our red bone marrow, and this is a type of bone marrow that produces our blood cells. Oh, so important. The compact bone, and we had that medullary cavity in the middle of the diaphysis, that's where we store yellow bone marrow. But here in the ends of the bone, in between the spongy bone openings, that's where we store the red bone marrow. And red bone marrow produces both red blood cells and white blood cells. Really, 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 really important. I've already introduced this. We talked about, I'll put in black. In black is the compact bone that runs the length, the dense compact bone that runs the length of the diaphysis. And of course, the compact bone is really strong to up and down forces. But where do we get our side-to-side ability? It's all about the trabeculi and the spongy bone. So the spongy bone, I'm going to put in red, right? It's up here, it's also down here. The spongy bone is much stronger, making a longer arrow, much stronger from side to side and twisting forces. So, pound for pound, spongy bone is not as strong as compact bone. But even though it's not as strong pound for pound, the spongy bone, because of its looser arrangement and because it lays down in the line of stress that we put to the bones, it has the ability to give us a little bit of flexibility and give. And we need that in order to be able to withstand twisting, rotation, side-to-side forces. Because the bone is a little bit flexible. I mean, the strongest structures in the world are not just brute strength because of these vertical pillars, because that's only going to give you strength in one direction. So here, like in many things in the mechanical real world, the bone has the best of both worlds. We get a lot of overall strength from those vertical osteons. But then at the ends, we put in a little bit more looser arrangement of bone tissue. And because it lays down in the line of stress, it gives us some flexibility and give. Because the bone will actually bend a little bit from the ends when we put stress on it. And that makes it, all in all, stronger, because now we can withstand all sorts of directions of forces. See what I just said? Gives us the best of both worlds. Okay. All right. Now, remember, we have the epiphysis, right? The epiphysis is the end, and then the diaphysis is the middle. Well, between the two is something called the epiphyseal line. Here it's shown right here, kind of a clear area. And I'll erase it so you can see where I just did that. See? It's like a white, thick line. That is the epiphyseal line, or a growth plate. It tends to be near where the epiphysis meets the diaphysis. In this picture, it's not exactly where they meet. They meet a little bit lower, I suppose. But they're near where the epiphysis and the diaphysis meet. What we are going to find when we talk about bone growth, when our bones grow, think about being a little adolescent, a little baby, I should say. Our bones grow in length because we get taller. And the bones grow in length from the center out to each end. So bone's going to grow as we get taller from the center out to the ends. As we get a little further along in our adolescent growth, another little growth center opens up at either end, at either epiphysis. And then the bone starts to grow in. Well, guess what? Where they meet is the last place that bone grows. So just for drawing's sake, that's not accurate, but I'm just for drawing's sake. So we had bone growing from the center towards the ends, and then we had bone growth from the ends towards the center. Well, where they meet is what becomes the epiphyseal line, epiphyseal plate, or the growth plate. This area is the weakest part of the bone, particularly in children, because in children it's still quote unquote open. The growth plate is open when bone is still being laid down and you're growing in length. After we complete puberty, the growth plate closes and there's no more bone growth in length. All that's left is a white little line of where that growth area used to be. But for children, where this area is still open, it tends to be the weakest because we haven't yet laid down hard bone tissue. So it's common to have fractures and injuries. Here's some x-rays. I'm not going to ask you this specifically, but I really like the visual. So look on the left. We see these growth plates. Here's one. It's open. See that open space? Because here, there's no openings. There's no opening there. It's been filled in. So on the left is an adolescent. There's more space between the bones because they're still growing. And that growth plate is open. Growth plate is open. Versus as an adult, there's less space between the bones because our bones have stopped growing. And any area where there was a growth plate is now filled in. And that's the remnant of the growth plate, the epiphyseal line. Pretty cool. Okay, just another random piece of anatomy, but of course it's important. We talked about the covering of the overall bone called the periosteum. Well, covering the epiphysis is a layer of hyaline cartilage, sometimes called articular cartilage. So if you look at the end of this long bone, there's an area of white. It's almost like the end of the bone is wearing a glove. And that glove is a piece of hyaline cartilage, which is, as we know, cartilage is a little bit squishy. So this is in an attempt to give some cushion at either ends of the bones. And why do we need cushion at either end of the bone? Because that's where that bone is going to meet another bone. So instead of just having bone on bone, either end of the bone has this little cushioning so that when the bones meet each other, it's the cushion meeting each other, and we don't have bone on bone. So make sure you know it is hyaline cartilage, not fibrocartilage, not elastic cartilage, but hyaline cartilage. Okay, our last piece of anatomy would be the filler. So if I go back to the example of concrete and rebar, if we are comparing a bone like the femur to concrete in a bridge or something, there's the compact bone, vertical pieces of osteon for strength, just like the rebar. But we also have the poured concrete around it. And in this case, what we have filling around the osteons, not only do we have collagen, which is protein fibers, we also have a bunch of minerals. So minerals help to fill around the osteons, like concrete fills around rebar. And the biggest of those minerals, we store all of these in the bone tissue, but the one that we're going to talk about the most is calcium. Now, you already know one function of calcium is to give bones strength. Better drink your milk for strong bones because it has calcium. Okay. But calcium doesn't only function for bone strength. A lot of that calcium leaves the bones. So while calcium is stored in the bones, it helps to give the bone strength. But a lot of that calcium leaves the bones because we need it for all these things. So in other words, bone is like a storage bin for calcium. And while the calcium is being stored in the bones, it helps to give the bones strength. But the bones are always releasing some calcium. It's never going to be empty of calcium, but always the bones are going to be releasing some calcium, which then travel in the bloodstream because, and I've starred to, I'd like you to know, every time we do a nerve impulse, we need calcium. Every time we contract a muscle, we need calcium. So having a sufficient amount of calcium in the blood is really important because our nerves will use it, our muscles will use it, and a whole bunch of other things will use it. So kind of cool, right? The bones store calcium. They store about 99% of all the body's calcium. So it's a big storage tank for calcium. And the bones like it because they get strength from it. However, there's always going to be some calcium being released from the bones into the bloodstream. And that calcium traveling around the bloodstream is really important. It may not be a lot in quantity, but we have to have that blood calcium in order to do muscle contraction and nerve impulses. Okay, so here we go. Let's next talk about bone growth. So now we understand the general structure of bone. We understand the general functions of bone. Well, one important thing to talk about is how bones grow in the first place, and I've already introduced that to you, and then also how they remodel. Because always, we are in the process of remodeling our bones. Old bone cells die that are old and need a cane, and then we have to replace it with new. Okay, so let's talk about bone growth. And believe it or not, it can start from as early as the fetus, right? So here's a late-term fetus, and we can already see the beginning shapes of what the bones are going to be. Most bones in our body, almost all of them, grow and develop initially through a process called endochondral ossification. There is another type of bone growth called intramembranous ossification that some of your skull bones and then your clavicle, which is your collarbone, use. But don't worry about that because it's much less common. We're going to focus on endochondral ossification. Okay, let's break the word down. Chondro means cartilage. Ossify means to harden. So basically, our initial form, the initial little bone shapes, are made up of cartilage. So the same late-term fetus that shows the outline, this is what's going to become the humerus, this is what's going to become the femur, and it has like the similar shape, right? Well, they are made up of cartilage. So they're bendy. They're not ossified yet. They're kind of like Gumby, right? They're pieces of cartilage. And it's good that they're cartilage at first because kids are going to grow. So we need these structures to be able to move and grow. It also is good because they're bendy and can withstand more of the kids bumping into things. You know, have you ever seen a kid do something like fall or whatever, and you think, how on earth did they not break a bone? Well, largely, if they're young enough especially, it's because their bones aren't bones yet. They're cartilage. So they're able to be a little bit more flexible. So what happens is, in endochondral ossification, what begins as something that's entirely cartilage, right? Over time, we begin to replace it with bone. And then by the time that we're done, we have something that's completely, I'll use black. We have something that's completely bone. It's ossified for that strength. And we still have a little bit of that hyaline cartilage around the end for cushioning. So this is really the basics of endochondral ossification. Initially, our bones are formed in little models of cartilage. And over time, we replace the cartilage with bone. What's important is it begins at the center, works its way towards the end, and then it starts at the end and works its way toward the center. So initially, we have a little bone growth center in the middle, and it begins to lay down bone tissue from the middle out towards the end, further out towards the end as we get older. And then, in addition to having our centrally located bone growth center, we also develop bone growth centers in the epiphyses. And they will start to lay down bone from the ends in. The last place that they meet is the epiphyseal plate or growth plate. And once we are fully through adolescence, that growth plate closes. It's no longer open for business to lay down bone, and all that's left is a thickened cartilage area called the growth plate. You don't need to know the specific steps as it's written here, just the basics, that we start laying down bone from the center out towards the ends. As we get older, then we have bone growth centers in the ends that are lay down bone towards the middle. The last place they meet is the growth plate or epiphyseal line. Now, that's how they grow when we're little. So endochondral ossification is bone growth in length. But it ends at puberty, right? At puberty, the growth plates close and there's no more growth in length. After puberty, you're not going to get taller, really, because our bones are no longer growing in length. However, even after puberty, the bones can still get thicker or thinner. So it is possible after puberty for bones to get thinner or thicker and potentially grow in diameter. That growth in diameter is called appositional growth. You don't have to know that term, but you just should know the theory that even after puberty, when our bones can no longer grow in length, it is possible, if we do a little weight training, that's weight bearing in particular, for our bones to get a little bit thicker. Okay, now I mentioned this also, but I like to put it in slide form so you can hear it, you can see it, we can be sure that you're going to review it. There's a constant process of bone remodeling. And we can try and keep this as simple as it really is, even though some of the processes are more complex. The overall idea, the overall pattern is simple. You know, bone tissues don't live forever. Maybe a bone cell lives 7 to 10 years. So when a bone cell ages and it gets old and it can no longer do its job, your body will break down the old bone tissue. And for whatever bone tissue we break down, well, we need to replace it with new. So it's a constant process because not all bone cells turn 7 years old at the same time. So it's just a constant process where some bone cells in our body are getting old, we replace them with new. But then the next day, the bone cells over here get old, we replace them with new. In this process, we need to define the two basic players, osteoblasts with a B and osteoclasts with a C. Osteoblasts are the cells that build new bone. I think about B for build. Osteoclasts Clasts are cells that break down old bone. These are tough because it's one letter difference and it changes the whole meaning of the word. They're completely different cells. Ideally, we want to have equal osteoclast and osteoblast activity. So for whatever osteoclast activity, whatever cells get broken down through osteoclasts, we replace them with new bone being built by osteoblasts. Now, as we get older, we are not as good at this process. For most of adulthood, the rate of osteoclast and osteoblast activity should be about the same. Maybe after injury, the osteoclast activity goes up for a period of time because we're getting rid of damaged tissue more. And then after the damaged tissue is gone, then we have to do more osteoblast activity to build it back up. So there are minor fluctuations, but over time, in healthy adults, we tend to have equal osteoblast and osteoclast activity. Well, as we get older, we are breaking down more, so we have increased osteoclast activity. We're just not as good at maintaining these cells. They get older more quickly, and then we're just not as good at replacing with osteoblast. We still try, but we tend to not be able to have enough osteoblast activity to keep up. And one thing that can result in is osteoporosis. Everyone's heard of this, right? This is a weakening of the bone tissue. It tends to happen in spongy bone. So you can look at the top at a healthy spongy bone. Yes, there's some openings, but there's quite a lot of bone tissue in between. A weaker spongy bone, an osteoporotic spongy bone, has much more open space because we're not able to keep up with rebuilding new healthy bone. All right, here we go. What happens when things go wrong? Okay, you've probably seen a fair share of, or maybe even yourself experience one, a fracture, a bone break. These terms in the scientific community mean the same thing. Anytime we fracture a bone, we break through its tissue, same thing. Sometimes somebody might use a different term to indicate level of severity, but really they mean the same thing. Okay, yeah. So if we have normal bone tissue, this is the diaphysis, this is the epiphysis. We have compact bone lining the diaphysis with a medullary cavity in the middle, and we have our spongy bone on either end, right? All right. Well, what happens if there's an interruption to this bone tissue? Well, now we've had a fracture or a break. So instead of having a continuous bone tissue, now we have fractured bone tissue. So how is the body going to heal that? Well, it's pretty ingenious. The same way it was originally formed. So how bones heal is really based on the endochondral ossification model. Why reinvent the wheel when we just did such a good time the first time? What we're going to find out in the next couple of slides is that we initially fill this area with cartilage and then over time replace it with bone. Okay, let's break these down into some simple steps. You don't need to go crazy. When we have fractured bone tissue, the first phase is swelling, to no one's surprise. Another word for an area of swelling is called a hematoma. Because we've broken these blood vessels, because we've broken them, there's going to be blood spewing out. We've damaged other tissue, so there's a collection of blood and tissue known as a hematoma. But then, what do? We quickly fill the gap with cartilage. Some other fibers too, but cartilage. This is a Band-Aid. It takes time to build bone tissue. So we don't want to just wait until the bone tissue is ready and just leave these fractured ends just flapping in the breeze. So your body fills it with an internal callus is what they call it, but they basically fill it temporarily with cartilage. Fill it with cartilage. It tends to be more of a fibrocartilaginous filling than it is hyaline, but we don't need to worry about that difference. Just know that it fills it with cartilage temporarily. And then over time, we replace that cartilage with bone. And guess what? We first replace it with spongy bone. And this is actually how it works in our original bone growth anyway. I just didn't talk about it. But we originally replace that cartilage with spongy bone. And then over time, that spongy bone will harden into the type of bone tissue it should be, which in this case is compact bone. To review these steps in a pretty basic way. All right, you do not need to know these types of fractures, as indicated by my pictures of fractures at the beginning of this presentation. This is an interest of mine, and I just like to talk about it. Ooh, a simple fracture is when you have a fracture in the bone, but the bones remain aligned, the bone edges remain next to each other, versus a displaced. This is crazy. This is a femur, probably from a car accident or skiing accident. The bones are no longer aligned, right? This bone edge is up here, and this one is all the way down here. Here, the bone edges, even though there's a fracture, they're still aligned. Again, you don't need to know these. This would be an example on the left of an avulsion fracture, usually a result of a ligament tear. So maybe a ligament that runs from here to here, that ligament tore and took a piece of bone with it because that ligament attaches to bone. So it was such a vicious tear that it took a chunk of the bone with it. A spiral fracture, to nobody's surprise, is a fracture to the bone in a spiral or a corkscrew way. This would usually be the result of some kind of twisting. A football player plants their foot and then changes direction and gets hit at the same time. The green stick is a funny name. Again, I'm not going to ask you these, but the green stick is like you've interrupted most of the bone, but there's still a little piece hanging on. Kind of like if you have a stick and you try and break it over your knee, and most of it breaks, but there's still one little edge hanging on. A stress fracture is such a tiny, basically crack in a bone that it's hard to see on an x-ray, right? So you do a bone scan, and these darker spots indicate areas of potential stress fractures. The stress fractures are much more common in an overuse type injury. A runner can get one in their femur. A runner can get one on their heel, their calcaneus. All right, you didn't need to know those, but I was just talking about them for fun. Okay, so the next part here is we're just going to talk about some of the bones themselves. We have over 200 bones. I am not going to ask you nearly anything close to those 200 bones. Instead, we're just going to learn the basic bones. It may seem like a lot, but really, in terms of anatomy, I'm asking you to know a very small amount of the bones that are actually there. Okay, when we talk about bones, there's actually different types. The one that we talked about in all our anatomy discussion was a long bone. Kind of like the femur. It's longer than it is wide. Most bones are long bones. It kind of looks like a penis. I am sorry. Short bones, like a bone of your wrist, are short. They may be kind of circular. A flat bone, like your sternum, is flat. And an irregular bone might be like your vertebrae, where we have these transverse processes, we have a spinous process. It's irregular. You can see I've only put a star beside the ones I'd like you to know. Long bones are the most common. Be able to give examples. They're longer than they are wide. Shorter bones are shorter. An example would be a bone of the wrist, a carpal bone. All right. In addition, we categorize bones into two categories. The axial skeleton. These are the bones of your thorax and abdomen. Like your main, not your arms and legs. So your skull, rib cage, vertebral column. These are in your trunk and head. Trunk and head bones. And their major function, instead of being movement, I mean, of course, some support, but their major function is more about protection. Our skull protects our brain. Our rib cage protects our lungs and heart. Our vertebral column protects our spinal cord. Versus the appendicular, which are the bones of the appendages, the arms and legs. These are less about protection and more about movement and structural support, allowing us to walk. Right? So here, the central blue are the axial, trunk, head, skull, and then the yellow, beige color are the appendicular. Notice two areas that sometimes people are like, well, does it belong to the axial or appendicular? The shoulder girdle, scapula, clavicle, and your pelvic bones. These technically are part of the appendicular. So really, the only thing that's part of the axial would be skull, rib cage, vertebral column. All right. You need to know the starred bones. On your critical thinking assignment, I'm going to be asking you to label. On a quiz and on the midterm and final, I'm not going to ask you to label. But I could ask you questions about these bones, about their location. So you do need to know them. You only need to know the ones that are starred. Really not asking you, it may seem like a lot, but I'm really not asking you, first of all, more than you can handle. But I'm also not asking you anywhere close to the number of bones there really are. So we're starting with the axial skeleton. And I'm going to move quickly here because it's very straightforward, okay? The skull has different lobes. Those lobes are connected, but there's no movement at these sutures. So we have the frontal bone up front, the parietal bones, there's one on the right side, one on the left side. Occipital is in the back. And the temporal bone is on the side by your temples. The facial bones. The mandible is your jawbone, but you're not going to say jawbone, you're going to say mandible. The maxilla is the bone kind of above your lips. The zygomatic bone is your cheekbone. It's right above it here. The zygomatic is, if a woman's going to apply blush, it's the cheekbone. Hanging down in your neck region is a bone called the hyoid bone. This is a pretty unique bone because it's considered free floating, which means that it doesn't attach to another bone. This only happens 3 times in the whole body. So out of our 200 plus bones, most of them attach to another bone. There's only a couple instances where a bone doesn't attach to another bone, and the hyoid is one of them. Okay, I try and give you plenty of pictures, and the good thing about this picture, I call it our multicultural skull, is because each bone is a different color, even though they all fit together to form one continuous skull. Make sure you review the vertebral column, right? There are 26 or 30 total segments, depending on how you count it. But you just need to know the basics. The cervical are the upper bones of your vertebrae, and there's 7 of them. The thoracic is the middle region, and there's 12 of them. Lumbar is the lower region. There's 5 of them. And then we have the sacrum. Sacrum is this one. Oh, wait a minute. Let me get my skills better. That's part of the pelvis. The sacrum is right here, kind of arched. And then the coccyx is, of course, your tailbone right at the end. You don't need to know that the sacrum can count as 1 or 5, depending on how you look at it. Don't worry about that. One way to remember this, maybe you read it in a textbook or maybe even online, I don't know, is breakfast, lunch, and dinner. The upper region, the cervical, has 7 vertebrae. You eat breakfast around 7 a.m. The thoracic region has 12 vertebrae. You eat lunch around noon or 12. And the lumbar, the lower region, has 5 vertebrae. And you eat dinner around 5 o'clock p.m. Okay. Good. That's what I said. All right. When we talk about the vertebral column, there are 2, basically C1 and C2 at the very top that have special names. So our very, very top cervical vertebra is known as the atlas, and it's shaped a little bit differently than the other cervical vertebrae. Cervical number 2 is called the axis because it has this vertical projection called the dens or odontoid process that fits up into the atlas, and it works as a pivot. The piece on the axis does. But just memorize that. Atlas is C1, axis is C2. The way that I remember this is alphabetical order. Atlas comes before axis, so atlas is higher, axis is lower. Basically, if you can just think of any little trick to help, that will help. Okay. Now, between the vertebral bones, here's one, here's another, are these cushions. Everyone's heard of the intervertebral discs. They sit in between the vertebrae. Each disc, if we were to look at it down below, has 2 parts. The outer region is called the annulus fibrosus, and it kind of has these concentric lines, annulus fibrosus, and the center region is called the nucleus pulposus. Nucleus means center, so it's not surprising. The nucleus pulposus is more watery, so the nucleus pulposus is more about cushioning, whereas the annulus fibrosus is a type of very thick cartilage for more about strength. And you can see up top, I have a picture of a s'more. Don't laugh, because I do believe that to be a pretty good analogy. Obviously not in terms of strength, because graham crackers are not very strong, but in terms of the mechanics of how they work together. The graham crackers are the vertebrae, the bones, and the marshmallow in between is an intervertebral disc, so it acts as a cushion. Okay, last thing for the axial skeleton, we have the sternum, which is the breastbone. We know that. And then we have the rib cage. There are 12 pairs of ribs total. The first 7 are considered to be true, quote unquote, because each of these first 7 ribs attach directly to the cartilage that attaches the rib to the body. You'll notice there's a piece of cartilage in between, which gives some give. So, because we need our rib cage to be able to expand when we breathe in. But the point of the true ribs is that the true ribs, that bone attaches directly to the cartilage. The false ribs are considered false because their cartilage has to attach to the cartilage above it before going to the sternum. Like some of these are so low that the bone can't directly attach to the cartilage, which goes to the sternum. So it has to connect with the cartilage of the one above it. And then the floating are in the back, 11, 12, and they just don't go all the way around. There's no cartilage at the end. Know these numbers. All right, we're going to keep it pretty simple, folks, with the appendicular skeleton. Here we have the upper body, the clavicle. Of course, you are not going to say collarbone. You're going to say clavicle. The scapula is our shoulder blade, but you're not going to say shoulder blade. You're going to say scapula. Humerus, upper arm bone. And then our forearm bones, the ulna is on the pinky side, and the radius is on the thumb side. So even if you rotate your forearm so your palm's facing forward or palm's facing backwards, no matter how you move your forearm and hand, the ulna is always on the pinky side. The radius is always on the thumb side. For the hand, you don't need to know the individual carpal bones. There are 10 of them. One of the fancy ways, well, not really fancy, as you're going to hear, A lot of times if you have to memorize a lot of bones like that, you think of a mnemonic device. The one that I learned for the carpal bones, some lovers try positions that they can't handle. So it outlines the 2 rows. There's 1 row here and 1 row here. So it goes scaphoid, lunate, triquetrum, pisiform. Some lovers try positions. Trapezium, trapezoid, capitate, hamate that they can't handle. Ha ha ha. But you don't need to know the exact. We're going to group it, all right? So the carpals is the term we use for the grouping of the wrist bones. I think about carpal tunnel, and that will help me remember C carpals for near the wrist. The metacarpals are the bones on top of your hand. Boom, 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 boom. And then the phalanges are the fingers. Fingers. Boop, 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 boop. Okay. Just know the groupings. When we look at the pelvis, again, I'm going quickly because it's very straightforward. When we look at the pelvis, we've got 3 regions. The ilium is kind of this top. It looks like an elephant ear to me. The pubic bone is in the front. So it's anterior. Pubic bone is in the front. The ischium is in the back. They're using purple. So look, I did include red for the pubis. It's the front. Can I find a purple to match this? Maybe like that? Yeah. Whereas the ischium is in the back, posterior. The ischium is the part that you sit on. So this is actually posterior. Just know those regions. Ilium is up top, like an elephant ear. The pubic region is in the front, lower front, and the ischium is the region in the lower back. Lower body, we're going to keep it simple, folks. Keep it simple. You can absolutely do this. Femur, big thigh bone. Tibia is the medial lower leg bone. Medial, closer to the midline. Fibula is the thinner lateral bone. And then we have names for groupings. Tarsals are your ankle bones. I think T for toe. Because remember, the carpals were the names for the wrist bones, right? Carpal tunnel near the wrist bones. Tarsals, we think about toe bones of the ankle. And then we have metatarsals, those are on top of your foot. And then we have the phalanges or your toes. Not so bad. Okay, we're going to keep chugging right along here. You may wish to take a break. That's absolutely okay. But I do encourage you to listen to this whole thing. It won't take us very long. We need to talk about joints because these bones come together and the joints is where we allow for movement. Okay, the fancy word for a joint is an articulation. What is a joint or an articulation? Any place where 2 or more bones come together. This is a really clear, I love it, MRI of the knee. This is the femur. And what I love about this view is that we get a really good look at the hyaline cartilage cushioning the edge of it like a glove. Down here we have the tibia and the fibula. Each of those also has a cartilage, hyaline cartilage covering. Over here we have the kneecap or the patella. Really cool, right? Love it. Okay, articulation or joint. Any place where 2 or more joints come to, 2 or more bones come together. We are going to divide joints into 3 types. Now, you might hear them also called, I prefer to use fibrous, cartilaginous, and synovial. You might also hear that, I didn't put it on here because I didn't even want to bother. You may also hear them called sympharthrosis, diarthrosis, amphiarthrosis. You may need to know that for one of your other classes, I suppose, but I prefer this way of separating them. I think it makes more sense. Okay, a fibrous joint is when You have bones coming together, but there's no movement. An example of this is the bones of the skull. And their connections, in other words, their fibrous joints, are called sutures. You may have the frontal bone connecting with the parietal bone. Well, the suture, the place where those two bones come together, is a fibrous joint. There is some connective tissue in that joint, but bottom line is there's no movement. It's still two separate bones coming together, but there's just no movement. Be able to define the movement possible and be able to give an example. The second example of a type of joint is a cartilaginous joint, as the name suggests. Here we have two bones, rib, sternum, connected by two bones connected by cartilage. That's why it's called cartilaginous. Bones that have cartilage in the middle. This gives very limited movement. It basically allows for a little give. Like I said in our example with the rib cage and the sternum, we have to have cartilage there because we need the rib cage to expand a little as we breathe in. And our most common, by far, is a synovial joint. Here is where two bones come together with fluid in between them. It's the most common, and it permits all sorts of movement: flexion, extension, abduction, adduction, internal, external rotation, circumduction, pronation, supination. Most of the joints that you think of, particularly in the limbs, the bones are joined together to form a synovial joint. We could really get into this a lot, but I'm trying to keep it as simple as I can because we have so much to cover. A synovial joint has to have this outer structure called a joint capsule. You don't need to know this, but there's got to be like an outer structure to contain the synovial fluid. Synovial fluid is going to line everything. And by the way, why do we have this fluid? Lubrication. These are joints that move a lot. And because they move a lot, and we have bone on bone, well, we have cartilage on cartilage because we have that hyaline cartilage, but still, just like pistons in a car engine need oil because of the constant movement for lubrication, so do our synovial joints need fluid. Okay, in and around these synovial joints particularly, we have tendons and ligaments. Make sure you review these definitions. A tendon connects a muscle to a bone. Ligament connects a bone to a bone. Sometimes there's a bursa, which is a fluid-filled sac, but you don't need to know that. If I go back to this picture, it shows us the ligaments. So here's a ligament. And even on top of that will be muscle tendons. Okay, some injuries or conditions to joints. These are pretty straightforward, but I think they're important to know. If you're ever out there and you see something orthopedic in nature, sprain versus strain. Here we go again with the spelling. One letter difference changes the whole meaning of the word. Sprain with a P, like a ligament pops. A sprain is an injury to a ligament. You can sprain your ACL. You can tear your ACL. You sprain a ligament. You strain with a T a muscle. Same thing as a muscle pull. We can have different joint diseases. Osteoarthritis is just the wearing away of bone tissue over time. You can see up top a healthy knee MRI. There's smooth lines on the femur, smooth edges on the tibia, versus in the osteoarthritic knee, some of these lines are a little bit more jagged. In the healthy knee, there's a beautiful free space here. That's where we're going to find our ligaments, our fluid, our hyaline cartilage. But in an osteoarthritic knee, the cartilage that lines the end of each bone has worn away. So instead of having that nice space for cartilage, that space is narrowed. You can see the space through here is much narrower than the space was up top. And inevitably, you end up with bone on bone. But rheumatoid arthritis is a whole nother thing. Rheumatoid arthritis is an autoimmune disorder, which means that it's genetically caused. And instead of the cartilage and the bone wearing away, in rheumatoid arthritis, some of these joint areas thicken. Maybe you've seen, particularly, and it's much more common in women. Maybe you've seen an older woman with rheumatoid arthritis and her hands, the fingers kind of point in one direction. The fingers point a little more this way than usual. And then there's this constant swelling. Look at all this swelling. And then the joint surfaces are thicker. So it really impedes mobility and it causes a lot of pain. Okay, look, I told you to be fast and I meant it. All right, study hard. If you have any questions, let me know.